Hello everyone. Today we're going to talk about sorting algorithm. As you may know, there are plenty of sorting algorithms, which may work well for a set of data that you may see. Today we're going to work on these two arrays that you see, array A and B, and we're going to see that each algorithm, what's going to be their performances on these two arrays. The first algorithm for sorting numbers can be binary search tree. So you may ask that how we can use the binary search tree to sort the numbers. So let's start with array A that we have here. So given this number array A, we start with the first number in the array, that is number 7. So we are putting that number 7 as a root of the tree. The next number is 3, so that goes to the left of the array because it's less than number 7. Next number is 2, so number 2 is less than 7 and also is less than number 3, so it goes to the left side of number 3. The next number is 9, and because 9 is greater than number 7, so it goes to the right side of number 7. The next number is 4. 4 is less than 7 but is greater than number 3, so it goes to the right child of the number 3. And the last number is 8, that is greater than number 7 but is less than number 9, so it becomes the left child of 9, that is going to be here. So now we created a binary search tree for this one. Now you may ask that how we can sort these numbers. If you traverse this tree in order, then you will see that the number are sorted. So in order, if you remember, the in order traversing of tree was the left child, the parent, and the right child of the node. So if you want traverse the tree using the in order, so in order traversing, then you'll see that the number will be sorted. So 2, 3, 4, 7, 8, and 9 going to be printed as the output of this traversing tree. Now let's see that how the second array B, will be shown as a binary search tree. So here we have the first number that is 1. The number 2 that is greater than 1, so it goes here. Then we have number 3, then number 4, then number 5, and then number 6. So as you see here, we have we created a tree for also this array. Again, if we do the in order traversing, so we can also have these numbers sorted. Although if we look at just the array A, array B, we already know that it's already sorted, because the number are in ascending order. But if in case that we don't know about the number of if the numbers are sorted or not, so we can create a binary search tree, and then have the in order to print the values that's gonna getting the values, and it's gonna show us the array in sorted order. So now, next we're going to talk about how creating a binary search tree will cost us, and what's the time complexity of inserting, removing, and also getting these numbers in a sorted array. So let's see that what's the time complexity of this binary search tree for different operations. So first of all, let's look at how we can insert a node in these trees. So on the left tree, or the tree that created for array A, almost the time complexity of inserting is equal to the log n. Before we had learned that the time complexity of the insertion in a binary search tree at the base case or the average case is equal to log n. So here this is almost log n. The time that we are going to insert a node. And the insertion is the time complexity doing the search, okay, because the insertion itself is just only one operation, but before doing the insertion you need to find the node or find the place that you need to insert the node. So indeed the insertion is actually this cost of the search, that in this case is log n, okay. But as you see on the others array or other tree that we have here, that is for array B, okay, the search is n, okay, here so it's log n, but here we have n because the array is already sorted. So every number that you are inserting, okay, is gonna be on the right child of the above node, okay, the previous node. So then here you see that for example, if we had another number 7, let's draw that number 7, so it goes here. So you need to do exactly 6 searches before reaching the number 7. So it's gonna be the worst case gonna be n, okay. So the worst case is gonna be n, okay, in a binary search tree, and the best case for the search will be log n. So now you may ask that what's going to be time complexity of building the tree. So in the worst case, because we have n numbers or n node, and the search operation takes n, so the worst case will be from the big O notation of n squared. That is when you have something like that, when you have something like the tree similar to the tree that we created out of the numbers B. But if we have some like numbers similar to what we have for array A, then we have n number and the search operation takes log n, so together will be big O of n log n, the building for this tree. And also for removing the number or accessing the number, again, this is like the search operation. So first you need to find the number, then delete that. So removing or accessing the number, the worst case will be big O of n, and on average will be log n, or the best case gonna be it's gonna be log n, not the best case, but the like the average case. On the best case for all of them, like the access for example for finding number can be the big O of 1, okay. For example, let's say you're looking for number 7, so the search takes big O of 1. Well, here if you're looking for number 1, the search operation takes only one operation, so it's going to be big O of 1. And again, when we are talking about the big O of 1, it doesn't mean that it's exactly one operation, but we mean that this is a constant time, okay. So that's gonna be like the time complexity of like using the binary search tree. So at the worst case, okay, it's gonna be big O of n squared in for sorting numbers. Other cases is gonna be n log n for like building the tree. Then we also have to like do the in order to get the number in a sorted format. So that's for now for how we can do this, how we can sort numbers using the binary search tree.